We can solve exponential equations using what we refer to as like bases. This is built around the idea that if we have a to the x power equal to a to the y power, then x has to be equal to y. If we know both sides of that equation are equal, the bases are the same, the value for a is the same. The only thing that's different are the exponents. That means the exponents have to also be equal to each other. And we'll see how we can use that idea in a few examples. In example 4, part A, we have 6 to the 7x plus 1 power equals 6 to the negative 7x power. In each case, the base is the same. That's what we need in order to be able to take advantage of this property. Since the bases are the same, that means the exponents must be equal to each other as well. So we can set 7x plus 1 equal to negative 7x and then solve. To do that, we'll add 7x to both sides and subtract 1 from both sides. This will leave us with 14x is equal to negative 1. Then dividing both sides by 14 will leave us with x is equal to negative 1 over 14. So when x equals negative 1/14, then that original equation is true. We want to apply that same idea in part B, but now we have a more complicated expression to work with, a more complicated equation. In these cases, what we want to do is identify the expression with the smallest base. In this case, that's 5, which is being raised to the 3x power. And that tells us what we want to do is try to rewrite everything else in the problem in terms of 5 raised to some power. We can start with 25, which we could express as 5 squared. That's being multiplied by 5 to the 3x power, which we can leave unchanged. And then we can rewrite 125 as 5 cubed. It may take a little bit of experimentation to find out how to rewrite all of the other values in the problem, but identifying that smallest base, which again in this case was 5, and then thinking about how to write those other numbers as 5 raised to some power will eventually get us to where we want to be. Now we can combine the two expressions on the left-hand side of the equation by rewriting this as 5 to the 2 plus 3x power. Since we're multiplying those two expressions together, the bases are the same, we add the exponents together, and that will still be equal to 5 cubed on the other side. Now our bases are the same, which means we can take advantage of that property and rewrite this as 2 plus 3x is equal to 3, or look at solving this equation. To do that, we'll subtract 2 from both sides to get 3x is equal to 1, and then dividing both sides by 3 will give us x equals 1/3. So when x equals 1/3, that original equation is true. In part C, we want to take the same approach. Again, a more complicated equation to start off with. So we look for the base with the smallest value, which in this case is 4, and start thinking about how we can rewrite the rest of the problem in terms of 4 being raised to some power. We can rewrite 1 over 16 as 1 over 4 squared. Which will be multiplied by 4 to the 5x power, set equal to, now we have 64. Again, we might need some experimentation, but we can rewrite 64 as 4 to the 3rd power. 64 is being raised to the x minus 2 power, so we still have to raise that new expression to the x minus 2 power. And now look at combining and simplifying some of our exponents. On the left-hand side, we have 4 to the 5x divided by 4 squared. So we can rewrite this as 4 to the 5x minus 2. And that will be equal to 4, which is being cubed and then raised to the x minus 2 power. So we multiply those exponents together since we have a power raised to a power. So this would be 4 to the 3 times x minus 2 power. And now we have two expressions with the same base, meaning we can solve 5x minus 2 is equal to 3 times x minus 2 to get our solution. There's nothing to simplify on the left-hand side, but on the right-hand side we can distribute through to get 3x minus 6. We'll subtract 3x to the left-hand side and add 2 to the right-hand side to get 2x is equal to negative 4. And then dividing by 2, we end up with x equals negative 2. So when x equals negative 2, the original expression is true.